Sorry about that. So for those joining the video, we sort of started late, my mistake. Okay, so we have this MCMC algorithm for spanning trees. It's the same as the lower walk on X. And so now the question is, how can we analyze these lower walks? So first of all, another claim I want to make that is in general the case is, what is our goal? Remember, our goal is to converge to, well, uniform distribution over spanning trees, right? But this is just going to be the same as pi n minus 1. We define pi n minus 1 to just be the distribution we're trying to get. This is how we chose the weights for the top level faces. So we want to get close to uniform. And my claim is going to be the lower walk always converges to this distribution. So it doesn't matter how we define the distribution of the top level faces. If you make the lower walk and you run enough times, it's going to converge this distribution. So my second claim here is going to be that the lower walk converges to pi n minus 1.
This probably requires it to be connected, right?
Yeah, I agree. This is also required. So this assumes, right? This assumes X is connected. It's a good point. Otherwise, there might be multiple stationary distributions. But in this case, we're actually going to prove later this is connected. So why this is it? What? Sorry.
So like in this context, connected means that you can get from a minimum spanning tree to any other minimum, or what does connected mean?
Yeah, good question. So there's no minimum here because we don't have weights. So it means that you can go from any spanning tree to any spanning tree by this process, removing an edge, adding an edge, removing an edge, adding an edge.
Mm-hmm.
Okay, that is it. So this way you can always go from any spanning tree to any other spanning tree. So this requires proof, but we're actually going to prove it later because this will be important for us later. But it's not hard. It's a simple combinatorial, claim. But yeah, this is what it means. But as I said, we're going to prove this later. But let's prove this in general. Well, actually, what I want to prove to you is that pi n minus 1 is a stationary distribution of the lower walk, which can just remind you is you were at level n minus 1, so we go down to n minus 1, and this is a lower walk. And why is this the case? Well, let's see. So let's take some face tau in x n minus 1, and let's say let's ask what's the probability. So we start by sampling a face based on pi n minus 1, and we take a single step. What's the probability that we're going to see tau after one step? Well, what's going to be the case? It's going to be, so take tau and see, and calculate the probability of reaching tau. Okay, so let me write this a bit more carefully. So it's clear to them. So we start from, I guess maybe I'll put it here as some tau. Okay, we start from tau distributed as pi n minus 1, and we take a step. Let's ask what's the probability that after this step we're going to reach some tau prime. Well, it's going to be how can we get to tau prime? Well, we must have started from tau, some tau, removed an element, add an element, and reach tau prime. So it's going to be the sum of all sigma contained in tau prime, whose size is the size of tau prime minus 1, right? And the probability we reached it is going to be pi n minus 2 sigma, right? This is the down step. And then we need to go back from sigma to tau prime. So it's going to be pi n minus 1 of tau prime over pi n minus 1 of X sigma. And we've already seen that, this bottom part here, the denominator, this just equals 1 over n minus 1 by n minus 2 sigma. So these two things cancel.
Other way, it's equal to n minus 1.
Oh, sorry. Yeah, it did the other way around here. N minus 1, sorry. You're right. Because the point we reach sigma, we have to sample from the link and then condition that actually get to sigma. So if you put this together, these two things cancel. We get 1 over n minus 1 sum of all the times sigma here. Sigma is in tau prime. The size of sigma is in this case n minus 2. By n minus 1 tau prime, and we have exactly n minus 1 ways of doing it. So this exactly gives us pi n minus 1 tau prime. So we get that the probability we reach tau prime is exactly pi n minus 1. So all that comes to say that there's nothing special about our case. Whenever we define a simplicial complex and we give it some induced distribution for the top face, the lower walk, if we start at this distribution, is going to come back to it. It's like a stationary distribution for this walk, and as long as the complex is connected, then it's just generic results in mixing that you have to converge after enough time in the limit of infinite time to this distribution. But this doesn't tell us anything about, well, how fast do we do it? So here we're going to use the notion of expansion. And the first thing we're going to do here is we're going to, the main lemma that we're going to prove is going to be the following lemma. So X is going to be our complex from before. We're going to prove that X is a one-sided zero local spectral expanded. Okay, that's going to be the main place where we're going to use the structure of the spanning trees. And this result I told you about metroids is basically by generalizing this lemma to say this is true not just for X coming from spanning trees, but it counts for any X associated with the basis of a metroid. But the proof there, unfortunately, is less combinatorial, it's more analytic, so we're not going to show it today. So what do we need to prove? So we're going to apply the trickling down theorem. So we need to show two things. We need to show, well, one is that if you look on faces of maximal level -2, right, then they're all zero local spectral expansion. So for any sigma in X n minus 3, X sigma is draw this way. Lambda 2 X sigma is at most 0. Then this is a graph now. And second is that for any k at most n minus 3 and sigma in xk, X sigma is connected. Right, and in particular, if we choose k to be 0 and sigma to be the empty set, we show that this entire complex is connected, which is what we needed for this mixing result. Okay, so once we establish these two facts, then we just apply the trickling down theorem, and this entire complex is a zero local set spectral expander. Because remember, 0 had this special property that in general, so this is just a reminder. So in the trickling down theorem, you always have gamma over 1 minus something gamma for some bound d. But if gamma is 0, this is just 0, right? So this is actually a very nice thing about this trickling down theorem. It's just if gamma is 0, then just stay 0 all along. And if you don't get worse bounds. That's really nice.
Shahar, is it immediately obvious that if the graph underlying the complex is connected, then the lower walk at the top level of the complex is connected? 'Cause that's what you need, right?
Yeah, but
I mean,
what,
we
what
are
do
going to
you-
prove it's connected because we're going to prove it has a spectral gap that's
that's true also.
maybe that's
Yeah,
obvious.
you're right. I think you're right. Yes, it doesn't show it. You're right. It doesn't show it directly. Yeah, I guess we do show it indirectly because we know it has.
We'll show it later indirectly.
Yeah, but the same ideas in the proof we will also show that. I mean, in the same proof ideas to show it also.
That's true.
Okay, so let's analyze. Now, this is going to be a completely combinatorial lemma that doesn't really have anything to do with each part with a high dimensional expansion, but together, they're using this trickling down theorem by Oppenheim. They give us this sort of complex viewpoint of this process. So let's start with one. So what do we have? So let's fix sigma in xn minus 3. So what is sigma? Remember, sigma is a tree with n minus 3 edges, right? So it's not a spanning tree. It doesn't have n minus 1 edges. It has n minus 3 edges. And what we're going to prove is the following thing. So we're going to claim, we'll use the following claim. Oh, sorry. Following thing. Let VW in x1, or let's say that's in x sigma 1, which means these are two edges. So these are nodes of the complex, but nodes of the complex correspond to edges in the graph. So there are two edges. So these are two edges that I could add to sigma and it would still be a tree. Then, 1 second. Sorry. Let VW two edges such that I cannot add both of them. All right, so these are two edges. Each one individually I can add to the tree, still a tree, but if I add both of them, I get a cycle. So I claim then for every other node z in x sigma 1, well, which is not v and not w, any other node, what we have is the following thing. Vz is in x sigma 2, it can only is wz. Okay, so let's try to decode what it says here. So we're saying the following thing. So there's a tree here somewhere, right? So here's a tree. So I already have some tree here. This is a sigma. And it has n minus 3 edges. So there's two more I need to add. And then there are two edges I could add here. There's this sort of V edge, maybe I could add here. And there's this W edge I could add here. Each one individually keeps it a tree. But if I add both of them, it's not going to be a tree anymore. Now I'm clear for any other edge, Z, maybe this is going to be Z here. Either I can add both V and Z together. If I can add V and Z together and it doesn't span a cycle, it's tree, spanning tree, then I can replace V with W. Also WZ doesn't have a cycle. But if V and Z hasn't cycled, then also W and Z has a cycle. So it really says something about this cycle structure of graphs. But I'm claiming that once we can prove that we're done. Why? Because let's think about this graph, X sigma. X sigma has the following property. Take any non-edge in it. That's right here. So let's take X sigma. And let's take two nodes that don't have an edge between. So V and W. There is no edge between them. So then every Z is either connected to both or connected to neither. Like maybe there is a Z here that's connected to both, and then there's another Z prime that's connected to neither. And I claim that this property, this implies that X sigma is either the complete graph, so it has all the edges, or a multipartite complete graph. For example, a bipartite or a tripartite or something like that. So I'm not going to prove it. It's a simple exercise about graphs. But if you have a graph with this property, every non-edge, every other node is connected to either both or neither of these nodes, it must be either the complete graph or a complete multipartite graph. Okay. In particular, both of them have lambda 2 being atmosphere. Because again, I'm not going to prove it. It's a simple exercise in graph theory. So again, I'm going to leave it to you as an exercise. So I just want to establish this combinatorial claim. So let's see. So let's prove this claim. So again, let's fix V and W that do not share an edge between them. So fix V and W. So VW is not in X sigma 2. All right, so these are X sigma 1. So each one individually connected to sigma and still be a tree. I cannot have both. And then let's also fix some other node Z in X sigma 1, which is not the same as V and not the same as W. So then there are two cases. Case 1, I'm going to look on sigma union V, W, and Z. So I'm going to add all the three edges. I'm going to ask, is this graph even connected or not? Does it reach all the nodes? If it is not connected, that's the first case. So adding the three edges, I cannot, this graph is not connected. But in this case, also if I also sigma union VZ and sigma union WZ are not connected. Right? Because the moving edges cannot make a graph connected. So this implies that in this case, VZ and also WZ are not in X sigma 2. They do not form. If I add VZ, I don't get a spanning tree because it's not connected. And similarly for WZ. So this was case 1. Any questions on it so far? The second case is what if sigma union V WZ is connected. But in this case, I claim that sigma union VZ and sigma union WZ are connected. Why? Let's take sigma union VZ, for example, where I know that V and W must be honest. I know that, what do I know? So we know that Y. Well, what do we know? We know that sigma union V and sigma union Z are, they don't have cycles. Because they are nodes of, this is because V and Z are nodes of X sigma 1. So I can add them to sigma and I still get a tree, right? But also I know that sigma union VW has cycles, right? And this is because VW is not in X sigma 2. So this cycle must go through both V and W, right? Sigma union V has no cycle, sigma union W has no cycle. So sigma union V and W has a cycle, the cycle must go through both V and W. So I can remove either V or W, and I still reach all the nodes I could have reached without it. So if I add V, W, and Z, and I get a connected graph, I can remove either V or W, it will stay connected. But now because I have exactly n-1 edges, and it's connected, it must be a spanning tree. Okay? So again, even if you didn't follow all the details here, I mean, first of all, they're in the note, but also We just use sort of basic graph theory here to argue about that. So this finishes the proof of the first claim. This finishes the proof of claim 1. And now let's prove claim 2, and it's going to be a very similar proof. So you want to prove that every X sigma is connected. Okay, so now part 2. So fix some sigma in xk, where k is at most n-3. We want to show that X sigma is connected. That's our goal. So again, let's fix some 2 nodes here. V and I'll follow the notations of the nodes. V and W in X sigma 1. So what do we have? We have, so we begin. So let's do a picture here. So we start by having some tree here. And I'm saying there are two edges I could add to this tree. I can add this edge, let's call this V, and I can also add this edge, let's call this W. So I claim here that I can go, that the way of going from, this is sigma, that the way of going from sigma union V to sigma union W by only single step, removing an edge, adding an edge, and so on. While keeping sigma, I cannot change sigma. Sigma is the same, right? So we're not allowed to touch sigma because we're in the link of X sigma. So, sorry. So what do we show? So we're going to show the following thing. So case 1 is going to be very simple. Assume that VW is in X sigma 2. Now, I assume I can add both edges, and it's still going to be without any cycles. Then it's very simple because the edge VW is in this graph. So they're connected by a single edge. Right? That's very easy. So the interesting case is that if they are not connected by an edge, VW is not in X sigma 2. So I cannot add both. If I add both, I get a cycle. In this case, we will show that there exists some other Z in X sigma 1 such that VZ and ZW are in X sigma 2. So meaning there is another edge, maybe this red edge I can add here, Z here. So I can add Z to V. I can then remove V and add W, and both VZ and WZ are going to be without any cycles. Right, so in this case, there's a path in X sigma V and W of length 2. So in fact, what this proof shows is not only this graph is connected, its diameter is 2. Right? For every 2 nodes, either there's an edge between them or there is a path of length 2 between them, which is enough for what we need. So why is this true? So again, the proof is going to be very similar to what we've done so far. So, okay. So again, let's do this case 2 here. So we know tau is sigma, sorry, is some sub spanning tree. So it's some acyclic graph. We can add V to it, and we don't the cycles. So I claim that there exists some, let's call it tau, such that sigma union V union tau is a spanning tree. Let's just keep adding edges until we get to a spanning tree. And then we also know that sigma union V, we also know that sigma union VW is a cycle. And the cycle uses both V and W, because sigma union V individually has no cycle, and sigma union W individually has no cycles. So I claim that this implies that sigma union W union tau is also a spanning tree. Basically, because I can replace V and W, I'm not going to create new cycles, because the only cycle that goes for both V and W. Again, this is like a pure graph theory statement. And this again implies that we can connect. Now, if we choose any Z in tau, we'll do. Take any edge Z in tau. I can have V, add this edge, now get sigma union VZ, I can now remove V, add W, it's going to be similar in WV, still spanning, still going to have no cycles. Okay, so that's a proof, that's another proof. So again, even if you didn't fill all the details, I mean, first of all, the notes, and also we don't use any machinery from like, high dimension expansion here, just some basic graph theory. So overall, what did we prove here? So we proved that X here, which is a complex associated with spanning trees, is a zero local spectral expander. Okay. And now the last piece of the puzzle that we need is the following theorem. We'll start proving today, we'll finish next time. Let's see where is this. And here's going to be the theorem we're going to prove here that well, if X is a d-dimensional zero local spectral expanders, then the lower walk satisfies that if you look at the lower walk is going to be go down from D up from D minus 1. Second eigenvalue of that is going to be bound away from 1 minus 1 over D. So it's bound away from 1. And in particular, this implies that, itself it might not mix because we don't have any guarantee on the minimal eigenvalues, but it's a lazy lower walk mixes, right? Mixes in time, in, I guess, order D time. So once we can get any guarantee that the second eigenvalue is bound away from 1, if we add the lazy component to the walk that you saw in homework 2, we automatically get a bound on the mixing time of the lazy lower walk. So now the lazy lower walk would say probably have to do nothing, probably have to do a lower walk step. And this makes it fast.
It's slightly misleading to say O of D because the time in will be exponential in D, right? So it'll really be like D squared.
You're saying because of the size of the
yeah, because D is n minus 1 and the number of spanning trees is like n to the n. Right. So you'll have n log n to the n, which will be n squared log n.
So the size of X.
Yeah. Yeah. Well, log of
that, yeah.
Log size of X.
Yeah, in order, right. D will be a spectral gap, and then here you're going to have log of XD. Steps. So the D here comes from the spectral gap, and then this log XD is just a standard mixing in graphs, log the number of nodes. In this case, our nodes are going to be all the possible spanning trees, or in general, all the top level faces. Okay. Yeah, that's right. Thanks. But you see, the theorem has nothing to do with spanning trees. It says whenever you can show that your associated complex is a zero local spectral expander, automatically you get good bounds on mixing. So really, this theorem can apply as is if you switch from spanning trees to any other object that has, these bounds. Okay. I just want to also mention, before proving this theorem, the proof we're going to show to you is going to be Alev-Lau. But actually, this version was also known before. This was by Kaufman and Oppenheim, yes? That's correct, Max?
Yeah, this was originally proved by Kaufman and Oppenheim.
Yeah, but we're going to show the proof of Alev-Lau because we're going to, first of all, it's simpler, also it generalized to give us even more mixing results we're going to see later, only on Thursday.
The Alev-Lau proof also follows, I mean, we'll see, it's almost exactly the same as the proof we did for local spectral versus random walk expanders. Yeah. Vedant told me that he basically came up with this by reading that paper.
Nice. Yeah, it's much simpler, much more streamlined. Okay, so before proving it, just to make one quick detour. So the proof will rely on something called positive semi-definite, or positive semi-definite PSD matrices, which is a very simple notion. So the definition, so a matrix, let's say M is PSD if for any vector F, F is non-negative. Or equivalently, all the eigenvalues are non-zero. Because this is what's called the positive semi-definite matrix. So of course, to do that, you need this matrix must have eigenvalues, and I will not prove it here, but all the matrices we're going to consider are going to have eigenvalues. Like for example, they're going to be like it could be symmetric. And then we need to also be able to use this to compare two matrices. So given two matrices, let's call them M1 and M2 on the same domain of the same size. We're going to write that M1 is curly, well, I don't have to write this. So it's smaller than this PSD order. Yeah. I think what's the way I want to write this? Something like that. This curly smaller than if M2 minus M1 is PSD. Okay. That's going to be another definition. This is called the PSD order. It's a partial order of matrices. And again, this is equivalently by definition, equivalently for any vector F. If I look on F and 1F is smaller than F M2F. Okay. So we need these two definitions of what is a PSD matrix. The matrix is all non-negative eigenvalues, and one matrix is smaller than the other one in this PSD order if the difference is a PSD matrix. Okay, so we need these two definitions. And now we can use this to prove the theorem, this Alev-Lau theorem, that says, that in any zero, well, one-sided, this is also always going to be one, but it cannot be zero two-sided, right? This is one-sided. Zero local spectral expander, the lower walk has a gap from one. So now I'm going to prove this. So let X be a d-dimensional, one-sided, zero local spectral expander. So we're actually going to prove something stronger. So what we're going to show, the following claim, is that lambda2 of the k level lower walk, so dk u k minus 1 is at most 1 minus 1 over k. Okay. So we're going to show it for every k from 1 up to, not just k. So we only care about the k equal to d part for this theorem, but it's going to be easier to prove inductively for all the levels k up to 1 to d. And the main way we're going to prove it is we're going to use the following claim. It says that, well, we're going to look on two matrices. One is going to be mk plus, which is a non-lazy walk, upper walk of the kth level. And we're going to claim this is smaller than in this PSD order than u k minus 1 dk. And this is going to be in this PSD order. Okay. So again, let's remind ourselves, this is going to be the non-lazy upper walk. This is going to be the lower walk, both acting on level k. Let's say k. Okay. Let's first prove this claim and then see what's useful to prove the theorem. So first, I can prove this claim is just follows very, very similarly to how we applied Garland's method before. So with claim. So let's fix some function f in ck for this operate function k level. And let's look on, well, mk plus minus u k minus 1 dk and ff. We want to show this is going to be non-positive in this case. Well, we're going to apply Garland. So this is what it will be. What we'll just open in parentheses. It's going to be mk plus f minus u k minus 1 dk ff. Right? Just open in parentheses. And now we're going to apply Garland's method. So it's going to be the expectation over faces 11 1 less k minus 1 of what? Again, this is something we've seen before. So the first thing is going to be a tau ff, which is a non-lazy walk on the link, minus the expectation of this should be f tau. I guess this should be the restriction to the link. So once expectation of f tau squared. So this is the claim we've seen, I think, at the last lecture, the one before it. It's just Garland's method. One of the versions of Garland's methods we've seen. And the point is this is automatically going to be non-negative, because what do we have here? Each one of us is a graph. And right, this is a graph. And here, again, I'm not going to prove it here, but you're basically decomposing f on the tau to all the eigenvalues. This we subtract the top eigenvalue, all the rest are going to be with the assumption almost 0. So this is always going to be almost 0, just individually, link by link. Just because we assume that every link is a 0 one-sided local spectral expander. Okay, this is 0 again because x tau, because that's right, because lambda 2 of x tau is at most 0. But this is just really a statement about graphs. So this whole thing is going to be at most 0, which is exactly what we want to prove. So we had this sort of PSD connection between mk plus the lazy upper walk in level k and the non-lazy lower walk in level k. So now let's use this to prove our claim. So again, this is what we're trying to prove. We're trying to prove this lambda 2 thing. So the first thing is just, let's look on k equal to 1. K equal to 1 is trivial. So now I want to use this to show that lambda 2 of uk minus 1 dk is at most 1 minus 1 over k, and by induction. So the base case is going to be k equal to 1. Well, what is k equal to 1? Well, we have, what is d1 u 0? Well, actually, so claiming that this lambda 2 of this is the same as the lambda 2 of, flipping the operators. This is true in general. This just follows from the fact that in general, for two matrices, lambda 2 AB is the same as lambda 2 BA. So if you take any two operators and you flip them, you get exactly the same spectrum, except for maybe some zeros. So you have maybe more or less zeros, but everything stays the same. So you can always flip the operators. Now, what is this D1 U0? But this is just something that X on C0. It's just one eigenvalue, right? It's just a one. So anything other than the 1 must be 0. So this is going to be 0. And here we're not using any property of the complex. This is true for any complex. So the base case is trivial. So this only becomes interesting from k being 2 and more. So now the general case, the inductive case. So again, let's first use the thing we just proved. Let's look on this m k minus 1 plus ff. So let's here Sorry, maybe for doing that. So, okay, 1 second. Yeah. Okay, so let's say I want to prove this for k minus 1. Yeah, I don't know why we wrote it for k minus 1, not for k, but this is how we wrote it. So let me stick with what we have in the notes. Oh, I know why. So now what do you want to show? So you want to show, no, now I remember. So you want to show for k, you want to show this, you want to show for k. So you want to show this bound on lambda 2 for k, but this is it will be equivalent. You want to show that lambda 2 of uk minus 1 dk is at most 1 minus 1 over k, because like we said, flipping the operators maintain the spectrum. And now naturally we're acting on level 1 less. So now instead of analyzing the lower walk on level k, we're analyzing the lazy upper walk on level k minus 1. Right, again, this is going to be this is upper walk on level k minus 1. 1 second. Iris. Sorry. So what do we have here? So now we're going to connect this to mk minus 1. That is now more natural. So first of all, let's use our induction. Let's look on m k minus 1 plus ff. So we're going to fix some f on level k minus 1. And what do we know about this? We're using now this PSD ordering. We've seen this is smaller than uk minus 2, uk minus 1, ff. This is using this relation we've seen between the non-lazy upper walk and the lower walk on level k minus 1. And now we can use induction. This is by induction. 1. So this is just using induction to level 1 less, 1 minus 1 over k minus 1. Okay. So this is also, we're connecting the non-lazy upper walk on level k minus 1 to this lower walk on level k minus 1 by this PSD ordering, and this we use induction here. And now the interesting stuff here is, well, we know what mk minus 1 is. Well, we know that mk minus 1 plus, this is again the non-lazy upper walk on level k minus 1. Well, that's going to be exactly the same as uk minus 1 dk times some scaling factor. Again, we've seen it last few times. Identity, right? We've seen it. We can write the non-lazy upper walk as a linear combination of the lazy upper walk minus the lazy term. Right? We've seen it also last time. Now applying this on f, what do we get again? Now we're going to try to get the same expression here. So mk minus 1 plus ff, and just plugging it here is going to be k over k minus 1. ff, right? And remember that this is what we're trying to bound. This is what we care about. Analyzing the upper walk on level k minus 1. This is what we're trying to analyze. So now we just need to put all the pieces together and finish the proof. So what do we know? Also, in the samples here, I missed here. Sorry, this should have been, of course, normalized with ff. Right? It's a norm of f. So we just put everything together. So we get it. So you see, here's what we're trying to bound. And we can say this minus some term of ff equals some other terms in ff. And if you just put everything together, so I won't do it here, but so just reorganize and you get dk u k minus 1 ff is smaller than 1 minus 1 over k. And this finishes the proof. So again, there's some calculations here that probably it's better if you check on your own. So I really want to sort of maybe spend the rest of just giving the high level viewpoint of what we've done. So the main thing we did here is translated this question about MC algorithm for spanning trees to a question about a lower walk on an associated complex. The only places we actually used spanning trees was to show that this complex was a one-sided zero local spectral expander. And then we see this general technique so that any one-sided zero local spectral expander must mix fast. Okay. And again, there are calculations here, and it's probably more instructive if you read them in the notes instead of like following them here. Lecture, probably it's easier. But I wanted that you get at least a high-level picture of the lecture. And what we're going to do next is show that, well, how can we generalize this zero local spectral expansion? It turns out that this being zero is a very strong property. And when you have it, it's great, but many natural questions in algorithms are not zero local spectral expansion, something weaker. And what we're going to see next time is that actually this technique can be generalized to handle a more general family of objects. This will give us even more applications. So we're going to see that on Tuesday, and then on Thursday, we're going to generalize even more to study in spin systems. So we're going to see more and more, say, elaborate applications of high-dimensional expanders in analyzing sampling. Yeah, I think maybe now is a good time to stop and see if people have any questions. Yeah, I know this talk was a bit technical side, but again, I hope that you at least got the high-level view of what we're covering here, and again, the notes give you many more details.
I guess if I'll make a note from last time if there aren't questions about this time, which is that we discussed that I had made the statement about kind of matrix norms versus the spectral norm, and we were saying Shahar pointed out there has to be some kind of condition for this to be true, and I looked into this, and I guess I really meant that it can be replaced by anything called a submultiplicative matrix norm, which is just some condition that says that kind of the norm of A times B is less than or equal to the norm of A times the norm of B. As long as you have this condition, then the statement holds. So I thought that was worth pointing out.
Isn't that like Cauchy-Schwarz or?
Does this follow from Cauchy-Schwarz? I mean, Cauchy-Schwarz says norm of, yeah, I guess this is like matrix version of Cauchy-Schwarz. But it's not true for all norms. So I think it has to define, like, it has to do with, because Cauchy-Schwarz is for some inner product space or something, right? So I guess if you're defining your norm through an inner product space, then probably it's always submultiplicative. But you don't have to define a norm through an inner product space, I think.
How do you define a norm on a metric? Like let's say you just want to define like a trace norm, or some LP of the eigenvalues.
Yeah,
I don't think you can define
will
them.
always be submultiplicative.
That's true, but I don't think you can define it through an inner product space, because two matrices might be like in different bases.
Right.
That's very cool. Okay. Yeah. Thanks.
Next, maybe you can put some pointer on Piazza for that. People can read about it if they want.
Yeah, sure.
Okay. So I guess maybe we're done for today. So I'll see you all next time.